So at the end of the last video, we briefly mentioned that we have indeed completed our reflection component passes, and that means that we both have the diffuse and reflection components complete. And we said earlier back on a whiteboard a long while ago that our diffuse and reflections, their total contributions add to a value of 1. So now we need to deal with how we can combine diffuse and reflection such that they behave in this way to give us a total value of 1. And we're going to need to be dealing down in a compositing network because we've got our reflection component, we've got our diffuse component here as a combination of a number of passes. We need to work out how to combine them through compositing. And this is actually very simple. We can use in Houdini a blend cop to blend between 100% of our diffuse, giving us 0% of reflections, through to 100% of our reflections, which would give us 0% of our diffuse, and the total weighting is always equal to 100%. So we're always going to have a total contribution, if you will, of 100%, whether that's 50% diffuse, 50% reflections, or whether it's 100% diffuse, 0% reflections, it always adds to 100%. So we can create a blend cop, and we can wire the diffuse into our first input, the reflections into our second input. And now if we take a look at the result, with 0.5 we're getting both 50% of our diffuse, 50% of our reflections, and we can change this blend factor. So there's all of our diffuse, all of our reflections, and values in between. Now the end result we're getting might not look very realistic, but we have to remember, of course, that our reflections are perfectly crisp, and if we had a very strong diffuse contribution, chances are our reflections wouldn't be crisp, they would be blurry. But you can see we are indeed able to blend between the idea of no reflections and 100% reflections, and the diffuse always makes up the remainder of that factor. So we need to generate this 0 to 1 value which we can drive the blend factor with. But the interesting thing is that this number does not need to be constant for the entire image. It can actually be unique. It can be specified on a pixel by pixel basis, and this is very important because obviously we may have different objects in our render, and each object may need to have a different diffuse specular contribution. So let's demo this. Let's just create a file cop, and notice I'm not bringing in a particular file, I was just creating a file cop, and I'm actually going to revert this back to its default so that I get the default butterfly picture, and I can wire this into the mask input of our blend cop, and that is going to use, you can see we no longer have a blend factor, we now use the blend mask, and it's taking the alpha channel and using that to drive the blending. So let's look at the alpha channel, because we've got an interesting thing going on here where inside the butterfly we're taking heavy reflections and outside the butterfly we're taking heavy diffuse. So if we look at our butterfly and push A on the keyboard to look at the alpha, this makes sense. We've got a black value which we can think of as being 0, and that's giving us diffuse, just as 0 on our blend factor was giving us diffuse, and our white value is giving us a value of 1, just as 1 on our blend factor was giving us specular or reflections. The white in this alpha channel is giving us reflections, but we're not restricted to just using the alpha. We could use the red channel, we could use the green channel, and if we were to jump over we can take a look at that. So that's using alpha, but we could use red, we could use green, or we could use blue. So as long as we can generate some image that in one of the channels has a 0 to 1 value per pixel that determines how we want to blend, then we could use that to drive the mask input of this blend cop. And that's exactly what we're going to do. We're going to generate a render pass that into the red channel of that render pass we have this idea of a diffuse reflection balance. It's an idea of black giving us diffuse, white giving us a reflection component. And I'm saying black and white. Really what I'm talking about is a value of 0 giving us diffuse and a value of 1 giving us reflections, because of course it's in the red channel. So the image, if we looked at it as a color image, would go from black through to red rather than black through to white. So that is worth pointing out, just so that when we see our pass later on we don't suddenly freak out because we're seeing red rather than white. We're only going to be dealing with the red channel, therefore anything in blue and green is wasted information. There's really no point in outputting anything into the blue and green channels. So if we can generate this pass then that's going to be really useful to us. But the question, of course, then becomes, well, how are we going to generate this pass? How do we want to generate this 0 to 1 value? Well, the most obvious way is going to be a constant value for each shader instance that we create, which means that each shader applied to, obviously, unique objects is going to be able to have its own unique balance of diffuse and reflections, and that's going to be uniform across the entire surface of that object. Now that's useful, but we may wish for that balance to not be uniform across the surface. So instead of just having a constant value, it'd be really useful if we could use a grayscale image, if you will, apply a grayscale image as a texture to that surface. And we've seen something very similar before where we've gone between a color or a texture. We're going to do the exact same thing here, but instead we're going to go between a value and we're going to take the luminance of a texture. We'll discuss why we're using the luminance rather than just a single color channel when we come to that in a later video. But it's going to give us the ability to vary the reflection diffuse balance across a surface. And this is really, really useful because let's imagine we had a metallic surface, a shiny surface, but on that surface we had mud splatters. So we may have splatters of mud on a surface, and obviously where we have mud, we really need a high diffuse contribution, but everywhere else we need a high specular, high reflection contribution. And we could now use this reflection diffuse balance pass to blend between diffuse where we have mud and reflections where we don't, as opposed to having to model the mud, which really, you don't want to be modeling all of the mud and putting it on the surface as a separate object. It's just an easy thing to texture map, and that's a lot more efficient, a lot better way of working. So we've got this constant value, or we've got a texture, and again we've seen similar setups for doing a color and a texture, so it's nothing really too complicated going on there. And that's going to allow us to specify a reflection amount, if you will, a 0 to 1 value that determines how strong our reflections are, and how strong our reflections are determines by the nature of the way the blend works, how strong our diffuse is. There's actually another way that we may wish to control this balance, and it's very useful for simulating certain types of surface properties. So I'm going to jump over to the whiteboard real quick and bring up a new whiteboard, because I'd just like to, for a second, discuss plastics. So imagine a plastic object. Now plastic is really interesting because its underlying surface structure, due to the way it's manufactured, gives us a very interesting visual property. So I'm going to draw, and this is not a scientific diagram, this is a diagram to help explain our purposes. It's not a scientific diagram by any means. I'm going to draw a diagram that kind of represents the underlying structure of plastic materials. So let's imagine that this is our plastic material. What we actually have in our plastic material is that this block of material is actually a clear substance. So this is really a clear substance, and inside this clear substance are a number of coloured particles all suspended. So obviously this is down at a microscopic level, but we have a number of coloured particles, and these coloured particles are suspended in a clear substance, and this is what gives us the look of plastic. Now you may wonder, well, why is this of interest to us when we're talking about balancing diffuse and reflections? Well, let's think about what happens when light hits a plastic surface. Light comes in and hits a plastic surface, and it hits the clear substance first. And as we know from very basic physics, this light, based on the angle of the light to the surface, is either going to do one of two things. It's going to reflect off the surface, or it's going to refract into the surface. So this is scenario A, and this is scenario B, where it refracts into the surface. Now if it refracts into the surface, it's then going to travel through this clear substance, and it's going to hit one of those coloured particles, at which point it's going to reflect off of one of those coloured particles back out of the surface. So again, this is overly simplified, but it really is going to help to visualize why we need to deal with a certain type of visual property. So we have these two scenarios, one where we reflect off the clear substance, another where we refract into the clear substance and reflect off of the colored particles. And what do we see in each case? Well, if the light reflects, scenario A, then depending on the surface quality, we're going to see a reflection of the light source, and that's going to be at varying blurriness levels. The important thing here is that we're seeing a reflection. We're seeing, because it's a clear substance, a white reflection color of our light sources. This is a reflection component in scenario A. However, if it refracts, we're going to see the color of the colored particles, but these colored particles, they're all over the place. We don't know which ones we're going to hit, and that means our light is heavily scattered by those particles. That means that we can think of the colored particles as being our diffuse component, whereas a reflection, scenario A, is our reflections component. So that means that in scenario A we see a reflection, and in scenario B we see the diffuse color of the colored particles suspended in that clear substance. The interesting thing here is that with plastics, that balance now between diffuse and reflections is determined by our viewing angle to the surface. Plastic is more reflective at a glancing angle. That's when we get sharp light angles to the surface as opposed to steep angles. At a glancing angle, it's more reflective. And this is actually a property of a surface where the surface is more reflective at glancing angles than it is at other angles. It's actually true of all materials. The interesting thing is that in some materials where the reflection component is so high anyway, like metals, that the effect of this is so subtle that we can actually ignore it. However, the structure of plastic means that this effect is so predominant, it actually gives plastic its particular look, and that means that we cannot realistically convey a plastic material in our shader unless we take into account this idea of the balance between diffuse and reflections being controlled, being driven by the angle of the light hitting the surface, by our viewing angle, if you will, because obviously the angle of light that's entering our eye is determined by the viewing angle. And there's actually a set of calculations that can determine the reflection-diffuse balance based on the viewing angle, and they're known as the Fresnel equations. And we've already seen that Houdini has a Fresnel-VOP for calculating them. We just haven't been using that Fresnel-VOP for all of its functionality yet. We've seen that we have a Fresnel-VOP, and that VOP gives us some inputs, and we've seen that we have a normalized viewing angle input, a normalized surface normal input, and ETA, or eta, as we know to be, is actually the refractive index. So eta, or eta, however you want to pronounce it, is the refractive index. And that just comes from physics textbooks that refer to the refractive index as the Greek letter eta. And so on the Fresnel VOP we have eta as an input, or it's a parameter on the VOP that we can specify the refractive index with, and it's going to take in the normalized viewing angle, the surface normal, and it's going to use those in conjunction with the refractive index to determine whether we are reflecting or whether we are refracting, because it's the refractive index of a material. That's a constant property of different material types. It's the refractive index of a material that determines whether light at a certain angle reflects or refracts. Now, the interesting thing is that we then, out of the Fresnel VOP, get Kr, and that is the proportion of light that reflects. We also get Kt, that's the proportion of light that refracts. We've already made use of R, the reflected direction vector, and T is the refracted direction vector. R has been very useful to us until this point, but now it's Kr that is of extreme use to us, because it's telling us the amount of light that is reflecting based on the refractive index and based on our viewing angle. It acts as a 0 to 1 multiplier of how much light has reflected. Now, it's worth noting that whilst you can jump into physics textbooks and find out the refractive index of different materials and use that to drive the shader, that we're dealing with images at the end of the day, and we're dealing with an artistic field at the end of the day. And that means that if a non-scientific value is giving you a visual result that you like, then that's perfectly valid. Just because we're dealing with plastic and plastic has a certain refractive index, if a slightly different refractive index is working for you on the shader, there's nothing wrong with that, as long as the visuals look like plastic at the end of the day. It's also worth noting that when you look in textbooks for refractive indices of particular properties, you'll often find that the refractive index is listed in a manner that won't actually be directly applicable to this parameter, because this parameter, despite being labeled as refractive index with the name eta, it's actually a ratio of refractive indices. It's the ratio of the refractive index of the viewing medium, which for almost all cases is air, is what are our eyes in, what is the camera in, compared to the refractive index of the material that we are rendering. And so we're going to have the refractive index of the viewing medium, which for air we can just pretend is a value of 1, it's very close to 1, divided by the refractive index of the material that we're rendering. Let's say for plastics, glass and the likes, 1.5 is a very rough approximate, and that actually gives us the eta value that we need to specify on the Fresnel VOP, as opposed to taking just 1.5, which is the refractive index of the material we're rendering. So it is worth noting that most refractive indices, when they're listed, are going to be numbers such as 1.33 for water or 1.5 for glass and plastics. We actually need to do 1 divided by that value when we specify that on the Fresnel VOP. But this is really useful to us because we've now got this output, this KR output, that we can use as a multiplier. We've also got our constant or our mapped reflection amount values, and if we can somehow combine those, that's going to allow us to balance between our diffuse and our reflections. So we've got our KR, which is our Fresnel-driven reflection multiplier, and we've got our reflection amount, which is our texture or constant color based reflection multiplier. And if we can blend between these in some way, or use one to modify the other in some way, that's going to be able to give us the pass that we need to drive our blend cop with. So we need some way to specify how much influence the Fresnel value has, because of course some materials need to use Fresnel, some materials don't need to use Fresnel, so we need some way of specifying how much influence it has, and then we need a way of influencing our reflection amount based on that Fresnel value. So let's tackle the latter part first. If our reflection amount, say, was giving us, let's say, 50% of reflections and 50% of diffuse, but our Fresnel was saying that we're at that viewing angle seeing 100% of our reflections, so that means that reflection amount was 50% and our KR was 100%. Well, that means as an output we really want to have 50% of our reflections, because what we want is 100% of our 50% reflection amount. We want 1.0, 100%, times 0.5, our 50%, is going to give us a 0.5 result. And that makes sense, because if we're being specified by the surface property that this surface gives us 50% reflections, 50% diffuse, and our viewing angle is saying of the reflections we're seeing, we're getting 100% of them coming back, well, we're getting 100% of our 50% coming back, and so we're getting 50% of our reflections in terms of the balance between reflections and diffuse. However, if we had 50%, but then based on our viewing angle, our Fresnel was saying no, in actual fact we're getting 0% of our reflections because our viewing angle is determining that we're not getting any reflections coming back to us, we then need to take our 0% of our 50%, and that's going to give us 0. So the result there is going to be 0%. And again, that makes sense because we're saying we want none of the reflections, even though our surface property says that we should have 50% reflections, 50% diffuse, we don't want any of the reflections, therefore we want 0% of our reflections. So we can take our Fresnel value and we can multiply it with the reflection amount, and that will give us the final value that we want. So we can say we've got our KR and we've got our reflection amount, and if we were to multiply those together, that gives us our final result. But in this kind of setup, our Fresnel is always having 100% influence. That means even on a metal where we wouldn't necessarily want to have our viewing angle affect the amount of reflections versus the amount of diffuse, we'd be having 100% influence. And we don't necessarily want this, so we need some way of specifying how much influence the Fresnel has, and we're going to do that with a Fresnel influence parameter. So let's think about this. We saw earlier that when our Fresnel had a result of 1.0, we had absolutely no influence on our reflections. Whatever was coming back from the reflection amount was what was being output in our pass. But when we moved towards 0, we were having absolute influence over our end result. So if we could blend between whatever KR was coming back as and a value of 1 based on this idea of a Fresnel influence, then we could determine how much influence our Fresnel actually has over the final result. So when our Fresnel influence has a value of 0, we want our Fresnel to have absolutely no influence. That means we need to output a value of 1. But as we move from 0 up to a value of 1 with our Fresnel influence, we want to output a value of KR, whatever our Fresnel happens to be. So we can blend between a value of 1 and a value of our Fresnel, our KR, based on the idea of a Fresnel influence parameter. And then if we take that value and use that instead of KR to multiply our reflection amount, we're going to be able to take account of this Fresnel influence and use Fresnel influence to bring in and take back how much influence our Fresnel is having over our reflection diffuse balance. So it could be very useful to specify our Fresnel influence as a constant value. It may also be useful to specify it as a texture. That may be something we want to change over a surface. And again, this is something we've seen before, so there's nothing really new being covered there. And so we're going to set up a network that allows us to specify Fresnel influence as either a texture or a constant value. And basically the resulting combination of our reflection amount, of our Fresnel, and of our Fresnel influence is going to give us our render pass that we can use to blend between diffuse and reflections. And that render pass is going to be, as I scroll down to find some room, our diffuse, reflections, balance pass. So this is our final render pass that we're going to be creating, and that render pass is going to drive the blend cop to allow us to blend between diffuse and reflections, and it takes into account the idea of a reflection amount, the idea of a Fresnel driven value, and the idea of a Fresnel influence. And all three of those are going to be key to determining the final value for our diffuse, reflections, balance. So hopefully everything there made sense. If anything's a little fuzzy, we will be recovering certain aspects of this as we implement it. So I would urge you guys to just keep on watching the videos, and hopefully when we implement each of these areas, things will become very clear as to what's going on. But that's an overview of how we're dealing with balancing our reflections and our diffuse based on both a material parameter in terms of does the material have a heavy diffuse component or a heavy reflections component, and a viewing angle attenuation of reflections based on the Fresnel equations as well. So that is going to conclude this overview video, and in the next video we'll begin the implementation of this render pass. Thanks a lot, everyone.